Hey everybody, welcome back to 113. Give me just a second. I need to make sure that my pen is calibrated, and then we will go ahead and get started. In answer to the question over in chat that somebody just asked, does submitting the petition for the major requirement waiver, is that valid for all of the classes or just 113? Technically, you have to ask for it for each one of the classes, but you can provide just a single application, a single petition, and just note all of the classes inside of there. You don't have to submit a separate petition. In fact, as the person who has to approve those petitions, please don't put 5 different petitions for 5 different classes. You can just put them all together into one petition and just list the classes inside of that single petition. But if you've already submitted a petition and it only had one class approval on it, then you'll need to submit another one with approval for the other classes that you're interested in doing the pass, no pass. And just as a side note, since that did just now come up, don't forget that submitting the petition is not the same thing as switching over to pass, no pass. To actually opt for pass, no pass, you have to do that through WebReg. The petition just gives you the permission to have something like that on your transcript when you're all done. Will there be office hours during finals week? Yep, we'll have office hours during finals week. I did have to cancel office hours tomorrow afternoon. Mir has a grooming appointment. He's, if you don't know, some dogs have hair that doesn't just naturally fall out when it gets, to its length. And so long hair can actually be dangerous for some dogs. They need to have their regular haircuts. And he needs to have his regular haircut because he is coughing up hairballs, which is not good for a 13-year-old dog. For the final project, where do we place the drawing concerning the 2 reactors on top of Warren Mall? Yes, that should go in your reactor design section. So you can add a little subsection after you did a CSTR and then you did a PFR, and you can add another little section after that. I suppose in the conclusion is fine too if you want to put it there, as long as we can find it. The grading scale is not posted. I just finished that up right before class, but didn't have a chance to post it. So it'll go up after class along with all of the notes from today. Along with also, I'll post the function that I use to calculate your grades, bonus point on your final project if you can find a mistake in there. Because it's really important to not have a mistake in there. It is your grade. So look through it and then make sure it matches what it says in the syllabus, right? We're going to drop a homework. We're going to drop the lowest 2 quiz grades, and then everything else gets scaled as it shows inside of the syllabus. So that function along with the grading scale will get posted after class. The grading scale will be fixed. So once I post it, it's not like it will get changed again as it goes, further and further along. CAPE incentive, I don't have any CAPE incentives put aside for that one. So our topic for today. So last week, John and I went over various forms of regression analysis, which is a way of taking a set of data that we have and trying to match it to some sort of an equation like a rate law or something like that, so that we can then presumably use that information to help us design reactors or understand a reactor or something like that. And so we've got through part of that, which is how do I actually do the statistics of it, right? And the statistics mainly came down to two functions, right? It came down to either the linear one, which was fit LM. So this was for linear models. Right, and we said that a linear model means something a little bit different than what it sort of historically has meant. It's not that it's linear in the predictor variables like X or C or whatever. It's linear in the coefficients. And so something can be, nonlinear in the independent or in the predictor variable, but still linear in its coefficients. So for example, the polynomials that we're used to seeing for heat capacity in liquids and gases and things like that, they usually come as like fourth order polynomials. Those are linear for the purposes of regression analysis because they are linear in the fitted coefficients, even though they're nonlinear, in temperature. And then the other function that's sort of a corollary to fit LM is fit NLM, which is a fit nonlinear model. Right, so this was for our nonlinear model. So nonlinear models are things that involve like exponentials and stuff like that, or we don't really get to sines and cosines, but mostly exponentials show up, although we get some pretty weird nonlinear stuff, so they do definitely show up. The part that was missing with both of those was how do we actually link those to experimental data for a reactor? The approach to that kind of varies with the type of reaction that you're doing. The one that we're going to look at is experimental data from a batch reactor, mostly because these tend to be the ones that you encounter first. If you're doing an experiment, batch reactors tend to be the ones that you, like an experiment in a lab course or for a project or something like that. Batch reactors tend to be the ones that are most approachable because you don't have to worry about pumps and valves and flow meters and all sorts of stuff like that. But they're also really useful, not just like in an educational sense, but from an experimental sense, they can use very, very small volumes. And that's obviously beneficial if your experiment involves chemicals that are quite expensive or hard to come by or something like that. You can also have very good control over the reactor settings when you do something like that. So it's very easy to get a batch reactor to be well mixed and to measure its temperature accurately without having to worry about lots of variations due to flow parameters and things like that. So in terms of statistical analysis, the thing that we're going to look at is a batch reactor. All of the batch reactors that we're going to look at are going to be isothermal and isobaric, only so that we can keep the attention right now on the statistical aspect of it, rather than the complications that come from, as we've already seen with our other reactors, having things be non-isothermal and non-isobaric. The approach for a non-isothermal or non-isobaric batch reactor is quite similar to what it is for the other reactors. It's just not anything that we really need if our emphasis is going to be on rate laws and things like that. All right, so here's our little batch reactor. The volume of stuff inside of the batch reactor, which I'm going to show it as a liquid. That's what the little wiggles there mean. But it does not have to be a liquid. It can be a gas if you want. If it's a gas, you kind of have to worry about pressure effects and stuff like that. So we may not bump into any gases, but there's no reason that a batch reactor can't be made to operate with a gas. Normally, if we had a flow, I'm going to draw a line here, but I suggest you don't draw the line unless you have an eraser. Normally, when we would have a flow coming in or a flow going out, we would represent the amount of material coming in as lowercase n sub I 0 coming in and lowercase n sub I with no subscript going out. In order to contrast those, remember these were units of something like moles per second, or kilomoles per hour, or whatever it is. With a batch reactor, there's nothing going in and nothing going out. And so we need a way to distinguish between the moles that may or may not be entering a control volume by a flow and the moles that are actually inside of that volume. It used to be in some of our other classes, you may recall that we denoted our flows with dots. So there used to be little dots above each one, but since like 90% of this class is flows, we've been omitting the dots the whole time. But now we're in a situation where we need to distinguish between the two of those. So like I said, you shouldn't have actually written that because I'm going to erase it all right now. So to distinguish between moles being carried into or leaving a control volume and the number of moles actually inside of that volume, we represent the latter with a capital N sub I. Right, so N sub I is however many moles happen to be within that control volume. The control volume that we would deal with here is whatever that liquid is, right? And that's the control volume here is the same as the volume, right? It's the same thing. There's our control volume. We can do similar material balances for a batch system as we can for flow systems. So it's still in minus out plus change is equal to accumulation. But since there is no flow, there is no in and there is no out, which makes it kind of nice. And so the accumulation term is perfectly balanced by the change. And you can do the taking the limit as a small slice of time goes to 0 in the same way that we did for small volumes of like PFRs or small weights of catalyst going to 0. Here you would do the same thing except with time. And you would end up with the material balance for a batch reactor, which is this. So the change in moles of I, which is dNI dt, is equal to the rate R sub I times the volume of the reactor, or in this case, the volume of stuff inside of the reactor. And similarly to how PFRs and packed bed reactors have initial conditions in terms of things entering the reactor, batch reactors have sort of like true initial conditions in the sense that we know what the amount of moles are when time is equal to 0. And so these would be equal to Ni0. Ni0 being however many moles of that stuff is initially inside of the reactor. And so that actually looks quite similar to our PFR version, a little bit different, right? Because there's a volume term sitting over there. But this is our material balance for a batch reactor. And that's the only expression that we're going to come back to, or that we're going to use when it comes time to fitting rate laws. We might modify that a little bit depending on what we have been provided for experimental data, but we will only need this material balance on a batch reactor if we're going to do any kind of statistical analysis. That's not to say you can't use another reactor. You can use CSTRs and PFRs and PBRs and all that kind of stuff, but we're not going to. The approaches for those are more of the same, and I'm more interested in the general idea than anything else. How come we're using big N, which is molar flux, if there's no flux in or out? It's not flux in this case. So capital N is just how much stuff is inside of there. So this is the amount of I inside of our control volume. Yeah, we unfortunately, again, bump into the somewhat different nomenclature that's used. We have run out of letters again. In a mass transfer class, the capital N could represent a flux, but here it's not. So to determine a rate expression, which is what we're going to spend most of our time doing, it's the reason why we did the fit LM and the fit NLM last week. To determine the rate expression, we have about 4 steps, maybe 3.5, 4, something like that. The first step, which we're just going to say it's 4, but some of them are really short, is to guess a form for the rate, right? So that's R, which is the same as guessing a form for R sub I, right? The thing that we need in our material balance is R sub I. So if you guess a form of R, that's the same as guessing a form of R sub I. Presumably you have whatever information you need to move back and forth between the two of those. If the amount of I's is moles or concentration of I, how does the right-hand side change? That's a good question. What if it's not just moles? We're going to derive the other 2 common forms of those here in just a second. And that'll show you what happens if it's not just N sub I. So our first step is to guess R sub I. Our second step is to substitute that form of R sub I into the material balance. And this is actually the step we're going to do here in a moment. Your material balance may be written in terms of N sub I. It may be written in terms of C sub I, and it may be written in terms of XA. Those are all very common ways that we can write that material balance. So we'll just have to take a look at each one of those here in a moment. After we substitute that in, we evaluate the integral. This is the part, by the way, the evaluation of the integral step here, or step 3. This is the one that can vary a lot. In fact, you don't always need to evaluate the integral. It'll vary depending on the reactor that you're using and the form of R that you've chosen, which we're going to note as R sub I. So what I mean there is the entire world of determining rate laws and rate constants and things like that. It is not limited to get yourself a batch reactor, run the experiment, collect the data, and then substitute stuff into a material balance. There are other approaches for different kinds of reactors. And in fact, different types of rate laws are better evaluated with other reactors. But the batch reactor covers an awful lot of them. The last step is to fit data to the model. Right, and then this is the stuff that we were doing last week, right? So these are the ones where you would use something like fit LM or fit NLM. So that's where the stuff from last week fits into what we're doing now, is once we have that data, then this is how we use it. So let's look at different types of those material balances. And I say different types because of the type of data that we can usually collect. So common data sets. The moles N sub I are actually somewhat uncommon, mostly because we don't have anything that we don't have a probe that'll just tell you what the moles of I are. Usually we're more interested in like a concentration or a conversion because those are a little bit closer to what our actual probes can measure. The moles of I usually requires a couple of extra calculations, and so it's okay if you can calculate that, but you know it's not the most common because it's not very close to what we can measure. Another common one, or I would say probably one of the most common, is concentration. So concentration is usually collected as a function of time. So your data set becomes concentration versus time. Right, so you've got, say, a conductivity probe or something like that stuck down inside of your batch reactor. It's spinning around and reacting. You're watching the electrical conductivity change as a function of time, and you're trying to relate that to a concentration somehow. Maybe it's not electrical conductivity, maybe it's color. So if you think back to CENG 4, when we had the little cuvettes that were on our car, that was an example of using color as a sort of stand-in for concentration. If you were to somehow calibrate that thing, you would know then, or you would be able to directly relate color to concentration. And so there's several examples of that sort of stuff. pH is another one that's very commonly used to get concentration versus time. For a batch reactor, the relationship between concentration and moles is similar to the concentration or the relationship between moles and concentration that we saw for flow reactors, with one difference, right? What we have previously seen, actually, I'll sketch this over and, oh boy, I hope that didn't mess anything up. What we had previously seen was that the moles of I in a flow stream going into or out of something was related to the concentration in that stream times the volumetric flow rate, right? Maybe it was V0 if it was a liquid, or maybe it was just plain old V before. That relationship still holds. We just changed the nomenclature a little bit because it's inside of a batch reactor. So here we use capital N sub I is equal to C sub I times V, where the capital V is volume of the reactor. Oddly enough, we don't change the way that the C is that's on there. If you think way back to our well-stirred approximation in a CSTR, this concentration C it is the concentration inside the main reactor. It just so happens that the well-stirred approximation for CSTRs let us say that the outlet stream has the same concentration as what's inside the tank. So that's not really an approximation. That's just us using the original definition of C sub I, which is the concentration inside the reactor. The changes are on the other two sides, right? We're not talking about a flow system anymore. It's just the amount of stuff inside of a control volume. The amount of stuff is Ni, capital Ni, and the control volume is capital V. So when you have something like this, you can substitute in for your material balance and get C sub I V inside your derivative has to be equal to RIV. And then typically the V is constant. Again, you can get into some tricky situations like with a gas reactor where if you have not made it a constant volume, you can't do what we're about to do, but you've also made life a lot. Nobody actually makes reactors that look like those cylinder pistons that you're used to from CENG 102. Those they don't actually exist. We don't use those for reactors. So if you pull that V out because it is constant, what you'll end up with is that the change in concentration with any species I as a function of time, so dCi dt, will just be equal to R sub I, which is kind of nice because it has a certain simplicity to it. Oops, that's a terribly not straight line. There we go. This one is convenient because concentration is both something that is easy to measure, maybe a little bit indirectly, but it's usually one of the easiest ones that we have to measure. But also it's convenient because R sub I, the rate term, is usually a function of concentration. And so, we were going to have to do some kind of modification sooner or later, just because rate is usually expressed in terms of concentration. And this is a convenient way to do something like that. So that's one option. How do you know if you're going to use that one or not? It just depends on whether the data was given to you as concentration as a function of time. If it was, then you should probably come back to this expression. If it wasn't, then it was probably given to you as one of these other ones. Oops, that was supposed to be a straight line. The other common one that we see is conversion versus time. And it's, again, usually conversion of A, one particular species. It's not conversion of multiple species. It's conversion of A versus time. Yeah, the batch reactor makes the assumption that it's well stirred inside. And that's one of the advantages of a batch reactor is you can make it tiny, and then you don't have to kill yourself trying to get the thing to be well stirred. If the reactors are large, it can actually be very difficult to get them well stirred. But if they're, lab size or something like that, it's pretty easy to get those stirred. And lab size is where we take our kinetic data. You do not want to have, a cubic meter reactor or something like that, something the size of a car. You do not want to be finding out what your kinetics are on a reactor the size of a car. That's not good. So we usually use very small reactors to do that. Microreactors are actually a popular area of research because they require so little material, and we can get everything very measured very accurately. So if it's conversion of A versus time, we're going to make one limitation. Our limitation is that it's going to be a liquid phase. And the reason for that limitation is so that we can write that C sub A, which is the only C sub I that we're going to be typically interested in for one of these, is equal to CA0 times 1 minus XA. Right? We can't write that in all cases for a gas. So I suppose a better, other than saying it's a liquid, our limitation is really that V is equal to V0, or well, no, that's not actually it. Let's just call it a liquid. I was going to say the initial volume and the final volume, but it's going to be constant anyway. So we'll keep everything limited to liquids. It's not that this form doesn't work for other phases like gases. It's that there are often other terms that sit here that we don't want to worry about right now. Again, we're more interested in the developing the approach of finding the parameters, and then we can always come back later and add. We can always make it more difficult afterwards. So we're just going to limit ourselves to liquids if we're dealing with conversion. If you have this particular form, then our dCA dt, which we just wrote a moment ago, it's actually still visible. It's right above me. It's not above me, above my notes. We can replace this with CA naught times 1 minus XA, which will again be equal to R sub A. Right, so with conversion, we're always going to limit ourselves to, I mean, in this case, obviously a liquid, but also one particular component, right? Conversion of A, or whatever it is we want to have called A. So what we end up with is dxa dt will be equal to minus RA divided by CA naught. And so that will be, if we're given a set of data that is conversion as a function of time, as opposed to concentration as a function of time, we will probably come back to this form of the material balance. Here, the initial condition is that we know at time is equal to 0, that the initial conversion was 0, right? As opposed to this one up here, where all we know is that the concentration, whenever t was equal to 0, is equal to that at 0. It's usually not 0 itself. It's typically a number. So those are our major forms that we're going to deal with. Again, just with a batch reactor, we've now got 3 different forms. If we had like a non-isothermal batch reactor, we'd have to go even further. There's plenty of work that we can do with a batch reactor, and so that's why we're going to spend all of our time. Material balances are pretty easy on this kind of stuff because it's usually one of these 3. Just don't have in your mind that this is the only way to do it. There are other methods by which we can determine rate laws. But this is a good one. It's very flexible. It's also, as I said before, the one most likely that you will encounter as an undergraduate in anything. Like if you're working on the CAR team, if you're in a lab class somewhere, if you're in a research group somewhere, most likely the ones that you will encounter on sort of in a university is a batch reactor. We have other reactors, but this is a pretty common one. For concentration versus time, what's the initial condition? However much stuff you started with. So for example, if you're doing something that gets degraded by UV light, you would dump everything together, stir it all up, and measure the concentration before you turn the light on. And that's your initial concentration, however much stuff you started with in the reactor. And then you'd flick the light on, and that would sort of start your stopwatch. And that corresponds to time 0. So you need some way to already know how much stuff is in there. Usually it's because you just dump the stuff in there in known quantities and then calculate the initial concentration that way. An example that we're going to look at, and actually one that comes up a lot, this style of reaction comes up a lot. It's called Estera Fication. The reason it comes up a lot is because you can usually measure it with a conductivity probe, and conductivity probes on the general scheme of things when you're trying to measure a concentration are pretty inexpensive, and they're pretty accurate too. So esterification tends to be a common example of something that we can actually do without having to buy, a $250,000 GC mass spec or something like that. We can use a conductivity probe. And we can scale our conductivity probes down to the micro scale, so we can do this in microreactors too, which is nice. So the esterification that we're going to look at is esterification of a molecule called propionic acid. With butanol, which is just like methanol and ethanol, except it's a little bit longer. So propionic acid has a CH3 group and then 2 CH2s. And then our classic OH and double O carboxylic group. I'm going to change the H here. Is that? So this is our propionic acid. And then it's going to combine with butanol, which is just a long chain hydrocarbon with an alcohol group at the end. CH3, CH2, CH2, and OH, which, by the way, if you're in organic chemistry right now and you're worried about it, this is about as much organic chemistry as you will typically encounter, which is good. Oh yeah, sorry, I have too much on here. Oh, it's so hard to erase that. 1, 2, 3, 4. There, I counted up my bonds on carbon. There should only be 4 bonds on carbon right there. Thank you. Why do we have to take so much OChem then? So that you're comfortable with it, right? So that every time I give you one of these structures, somebody can point out, like they just did, that I have a mistake on it. That's why. I understand the question. I am not good at organic chemistry. I scratched my way through it, and I was happy. I was proud to do so. I wasn't just happy, I was proud. CH2, and then we're going to bond some stuff here. 1, 2, 3, 4. Oh, butanol is 4 carbons. See, there you go. I actually had that one in my notes. I'm not going to claim that you got that one because I did it wrong. I just copied my notes wrong on that one. But you're right, and it's 4. We're going to bond this with that long hydrocarbon, CH2, CH2, CH2. All you guys are showing me right now is that in the future, I just need to stick with the molecular formulas and not try to be so complete. So here's our butanol. We get some water coming out on the other side. This fella, the bigger one here in the middle, this is N-butyl, spelled it wrong, propionate. The reason that we would want N-butyl propionate is that this is a good solvent, but it also has a low vapor pressure, which is good if you are worried about the environment, which we are. Everyone should automatically be concerned about the about the environment. A low vapor pressure is a good thing because it reduces what we call VOC or VOX, volatile organic compounds. Volatile organic compounds. If you can reduce VOX, the number of volatile organic compounds you work with, that's good. It reduces the amount of carbons that make it into our atmosphere, which inevitably wind up somewhere that we don't want them. So this is a good one because it doesn't evaporate. It's got a low vapor pressure. It just kind of hangs out. The general expression that we're interested in here in terms of a reaction is A plus B goes to C plus D. There were some folks that actually collected data for this, which I don't have their full citation at the moment. But what they did was they dumped this stuff into a batch reactor. It was liquid phase, and then they collected it every 30 minutes. So it's a very slow reaction. And they went for 6 hours. And the data that they collected was the conversion of A, right, which was our propionic acid. And I'm just going to list these numbers here so that we can do the fit afterwards. 0, 8, 12, 17, 23, 27, 28, 33, 36, 39, 42, 43, and 44%. Right, so these were the conversions of A that they measured starting at time 0. So down here was time 0. And by the time they got up here, they were at 6 hours in 30-minute chunks, 6 or 6.5. I can't remember if they made it up to 6.5 or not, but they went in 30-minute chunks. So our goal is estimate K if R is equal to KCA. And we're going to do this in 2 ways. We've got about 12 minutes left, so we'll have enough time to do both of them. We're going to do this first by nonlinear regression. So the first one we're going to use is fit NLM. And the second one, we're going to do linear regression, which is fit LM. Right, and so we're just going to compare how could I approach this problem by using either one of those. We cannot always do both. The general breakdown of sort of the scope of problems that you can solve, if this is the world of problems that can be solved by fit NLM, then the world of problems that can be solved with fit LM with a linear model is a subset of those. So if you can do it with a linear model, you can definitely do it with a nonlinear model. But if it can be done with a nonlinear model, it can't necessarily be done with a linear model. But there are a number that are very easy to go back and forth with the two of them. They have advantages and disadvantages too. There's no inherently right or wrong way to do it. There's just differences between the two. There are recommendations, which we'll give you. So if we wanted to go about this in the first approach, which is fit NLM, this approach says we need a model for XA, which this XA is going to get a hat, right? Because this is going to be our model XA. And this is going to be a function of other XAs and time. So time, sorry, not other XAs, other coefficients like K. Right, we should be able to predict a value of XA given only the time that the reactor has been operating and the rate constant K. Why do we know that it's only K? It may not be only K. We know that it's only K in this case because the rate law that was given to us only has one parameter in it. If there was another K, like a forwards and a reverse K, we'd have to deal with that one as well. If there was, what other kind of parameter, an activation energy, pre-exponential factor, anything like that, we'd have to approach each of those as well. So given that we're working in conversion, our material balance for a batch reactor in terms of conversion is dxa dt. And if we just scroll up a little bit, that'll be divided by or equal to minus RA over CA naught. Minus RA CA naught. We can then substitute in our rate law, and then what we end up with is K times 1 minus XA. Right, subject to the initial condition that XA of 0 is 0. That is what steps 1 and 2 in our sort of algorithm, right? The first thing we do is guess the form for the rate. We actually didn't have to guess that. We were given that. The next thing that we did was substitute that rate into our material balance, which is what we did right here. And now with those two, we move on to the third step, which is to evaluate the integral. So we have to go ahead and evaluate this integral, which if you sort of are comfortable with your math, which I am not, so I solved it before class so that I didn't have to solve it right now. Log of 1 minus XA is equal to minus K times T. So there was a negative sign in there, but I pulled it over to the other side. And now I'm going to get XA is equal to 1 minus exponential of minus KT. Right, and so each one of these are hats, right, because this is the model. I'm usually not in the habit of actually carrying the hats everywhere, but technically these are the hats because this is a model. The values without a hat are the experimental data, and so that is our hat data. So if we were going to fit this inside of MATLAB, the way that we would do that, I'm going to switch my colors over to blue. If we were going to fit this in MATLAB, we would need our fit_lm call, which is model will be equal to fit NLM. And then we have to give the predictor variable followed by the response variable. And so our predictor variable in this case would be our time vector, and our response variable would be x sub a without the hat, right? Because those are our experimental data. We also have to give it a handle to our function, which is at fun, not fun. And we have to give it a value for k-guess. Right, nonlinear regression is an iterative process, and so you have to know where to get started, or fit NLM has to know where to get started, which will require an initial guess. The local function for the function that's defined here, that has to refer to this expression. Right, so we need to come up with a local function that basically encompasses that function, and so we would say something like function output, maybe we'll just call it out, is equal to a function. The inputs are classically called beta. It'll have to be in decimals. X will have to be in decimals. Let's see, so it'll be function of beta and time. Here our rate constant k will be equal to beta of 1. You don't have to call it beta. If we wanted to just pass in k right there, we would be perfectly fine doing that. The reason that I'm using beta here is to try to remind you of the link between the betas that are used sort of in general terms. The output of a lot of these functions will say something like b or beta or something like that. It's just a reminder to you that these are the fitted coefficients. Right, and then our output here has to be a vector of our model data. So this will look like 1 minus the exponential of minus k times t. Right, and so we would dump these two elements together, put them inside of MATLAB, take a look at our results, see how they look. If we do something like this, I'm just going to tell you one number really quick because this is the one that we're going to be interested in for now. I'll post the completed set of code for this as well so that you can see it. If we were to do this, the result is that k is 0.1096. If I originally said that we can do this by either the fit NLM or fit LM, so we can do it with either a linear fit or a nonlinear fit, we would hope to get close to the same thing if we take approach 2, which is to use fit LM, which is our linear model. So our linear model requires just that, right? It requires a linear model. This form that we had before, XA, is equal to 1 minus, what did I say it was, exponential of minus kt, XA hat. This is nonlinear. We know that it's nonlinear because the k shows up inside of the exponential, right? This part right here, the k being inside of there, that's the thing that makes this nonlinear. So if we're going to do a linear regression, we need to linearize this form so that it has, it's linear in the coefficients. An easy way to do that is actually, we end up with a linear form a lot of times when we're evaluating the integral. We actually had a linear form already, this form. Right, that's already linear. It's just we went one step further for the nonlinear model and expressed x directly, which was nice because that's our response variable. So our linear form down here, if we take this form, is natural log 1 minus xa hat minus kt, or is equal to minus kt. So this one is linear. if this is going to be our linear form, then what we're looking at over here on the left-hand side, this is now our response variable. Right? It's no longer just plain old XA. It's the natural log of 1 minus XA. The t over here is still our predictor variable. Right, but now this is linear because we can rewrite this as something like y hat is equal to minus k times x. Let's not use x since we've already used x, kt. Right, so this form is linear. Often we have to do that kind of a trick when we want to do a linear regression. The material balance itself very, very rarely pops out as a linear equation in the coefficients. And so we typically have to do some kind of a linearization routine like this if we want to be able to use linear regression. We're going to have more to say about that on Wednesday, but for now, let's just roll with it and assume that we're okay doing something like that. The MATLAB code for this, let's switch back to blue since blue is our MATLAB. Model will again be equal to fit, but this time it's fit LM instead of NLM. And then we have to provide the predictor variable and the response variable. And so our predictor variable will still be t. That hasn't changed. It's still time. But our response variable is no longer XA. It's now log 1 minus XA. And in MATLAB, natural log is L over G. Or sorry, not L over G, LOG, that is natural log. Yes, there's a comment in chat that engineers love to make everything linear. Yes, we absolutely love it. Actually, we try to make very basic things linear, and then the results get very, very nonlinear very fast. So you'll bump into that. If you haven't already in fluid mechanics or mass transfer or heat transfer, the underlying relationships, like at their very core, are linear. And then it's the multiplicity of the interactions that makes everything nonlinear, which is tough. We have to give one more input here, which I'm just going to write. Intercept as a string has to be false. And I'll point out why here in a moment. The intercept false part here is because if you look at our linear form here, there is no intercept, right? It's not the equation of a line. There's no constant term sitting out in front of it. And so there is no intercept. And no intercept means if you set time equal to 0, the response variable is also equal to 0. That's kind of a weird case. Linear regression doesn't actually like it too much when there's no intercept. But sometimes we have to force it to be that way. As a result of not having an intercept, what you'll see when you run the code after I post it is that some of the results aren't there anymore. But the important one is, which is that K is 0.1074. Oh, by the way, these all have units too of inverse hours. So this part here, the intercept false, that is because of the form that we have here, right? It doesn't have just a plain old intercept like a y equals mx plus b. The b in there is our intercept and we don't have it. So with that, we can compare. We got 0.1074 here, and we got 0.1096 up here. This was also per hours. Those are pretty close. They may not always agree. They'll be pretty close most of the time. It just depends on how good of a guess you can provide. But we'll talk a little bit about the advantages and disadvantages of a linear regression versus a nonlinear. If nonlinear works for everything, how come we just don't use it all the time? Hey, in an ideal world, we would, but we don't. Linear models have some advantages to them as well. So I'll wrap it up. It's 3:52. I went over by about a minute and a half there. Again, I will post the code that solves this stuff so that you can take a look at it. Although there is enough information in just what I've given here that you could give it a shot and compare your answers to what I've got. So as always, I'll stick around for a couple more minutes and answer any questions that you might have. But we are formally done with lectures, so nothing else new coming. If you take off, see you. Stay safe. We'll see you on Monday or Wednesday. Yeah, so those are two really good questions about beta. Do we have to define it first? You have to give it a guess, which is sort of like the same way that we give fsolve a guess. So yeah, something like that has to be defined first. How do you know the range? That's the really tricky part, is we don't always know the range. Often we have to try a lot of different things. We can often put limits on our guesses. So for example, we know the k has to be positive, and sometimes that can be a big change, but we don't always know. One way to get a guess for k is to actually do the linear regression first, on like a simpler model, or a similar model at least, because the linear regression doesn't require a guess. But it's tough. We may not know exactly where to get started. We might have to try different things. There's an example in chapter 13 of how do we just start picking numbers. We try like orders of magnitude and see what happens. No, the reactors for the midterm aren't supposed to have the same depth. Are not supposed to have the same depth. Yes, John, I can. Yeah, so if you change your guess for k, you will get different answers for k depending on how big of a change of k you provide it. And that's, I don't want to say that it's a feature, but it's definitely not a bug. It's the same way that we can have multiple solutions for CSTRs. We can have multiple things that we may not know whether it's a global minimum when we're minimizing the sum of squared for error, but the solver, the fit NLM, will get stuck in a local minimum near your guess, and it will say, well, that's the best I can do for your guess. We just have to try different guesses, and then use our engineering judgment to decide which of those guesses are good, and which of those answers are good, and which are bad. Yeah, the incomplete that I referred to in my email is you can basically tell me, like, I want to stop the class for 5 weeks, and you just get an incomplete, and then sometime out in the summer, you tell me, okay, I've got time to finish up the class. So we sort of start up the class again, and then you just get the grade that you would normally get. Incomplete's like a placeholder for your transcript, and then I just input the grade later. It has no permanent effect on it. It would in the intermediate, right? If you wanted to know what your GPA calculation would be missing a grade until I post that grade. So it's just kind of a placeholder to sort of pause the course for a while if you want to. That, if you're referring to question 1, that was my intent on question 1, because something was different on question 1 about the r-squared and the p-value. Some of the values were the same, but some of them should have been different, and that was on purpose. The question about the CSTR, I mean, any reactor can reach its equilibrium, but I'm not sure which CSTR you're referring to. If you're referring to the CSTR that's in the project, that reactor is probably not operating at equilibrium. It's operating at steady state, but equilibrium is not the same as steady state. You can operate a reactor at steady state that's far from equilibrium. But you can also try to get a reactor to steady state or to equilibrium if you make it large enough. So that maybe I don't understand the question 100%. Let me check. I guess I don't, if I replace the word equilibrium in your question with the word steady state in your question, I still don't quite follow your question. Maybe you could rephrase it. Yeah, I can see what you mean for a CSTR. I think the magical part of the CSTR is that we never pay attention to what's happening on the inside. And so what you can sort of visualize is happening inside of a CSTR looks something like this. If this is our big CSTR, we got stuff going in and stuff going out. It comes in at a liquid level here like this. But let's imagine that you are a blob of material. And so I'm going to draw a little mixer here. Let's say this is that's our mixer that's sending stuff around. If you are a little blob of material and you're out here, you get carried along in the pipe, right? And presumably you're not reacting. And so you look the same as you go along that pipe, right? There's no reaction inside of that pipe. Exactly how we stop the reaction in the pipe is odd sometimes, but at any rate, what happens is you as that blob of material then enter the CSTR here, but you don't just immediately get spat out over here. Your time spent in the reactor is because this mixer is stirring you around, right? So this mixer is actively moving. And so the path that you take inside of this reactor may take you over to here. It may take you over to here like this. You could go around back behind the mixer, come out over here. All this time that you're on this path, you're reacting because you are inside of the reactor. Maybe you come out through here, go around this a couple of times, not unlikely, like this. And then find your way out of the reactor over here. So for the CSTR, you spend some average amount of time inside of the reactor. Any of your neighboring fluid elements, so let's say there's another fluid element like this that's getting convected in, right? Those will follow a different path, but they will spend on average the same amount of time inside of there. So you could kind of imagine this as almost like a batch reactor for little tiny elements of fluid where you get pushed into the reactor, you spend a certain amount of time in the reactor, and then you come out the other side. Or somehow you get taken out. It is not guaranteed, though, that every fluid element will always spend the same amount of time inside of the CSTR. And that's actually a topic that sometimes we get to in graduate reaction engineering is what's called a residence time distribution. Residence time meaning how long do you reside on average inside of the reactor. That's what a residence time is. And so you're actually sitting inside of the reactor reacting, but everything is following a different path because it's all getting mixed up inside of there. And then you're just kind of collecting stuff that's coming out the side. I think the word that you're looking for is well stirred. And the well-stirred approximation says that the time spent inside of the reactor is the same for all fluid elements. That's exactly the opposite of, it's not exactly the opposite. That's the part that we sort of reinvestigate at the graduate level, which is to say, well, what if those do not all spend the same amount of time in the reactor? And how do we figure that out, right? If you're a red blob and you're getting convected into the reactor by the pipe, you may in fact skip almost the entire reactor and come out over here, having spent not very much time inside the reactor. That would be a violation of the well-stirred approximation. The well-stirred approximation says that they all spend the same amount of time in the reactor, and that's the key part of sort of quote unquote the magic behind the well-stirred reactor, is everything is spending time inside of the reactor. Yeah, I can see why. I mean, the packed bed reactor and the PFR are basically just tubes, right? You just shove stuff in and get product out the other side. The CSTR's advantage is that it's algebraic, so you don't have to try to solve a couple differential equations. But the algebraic expressions, as we have seen, can be every bit as difficult as the differential equations. It's harder to keep it operating the way that you want it to operate. You have to be careful with how you mix things. And so, for example, there's a lot of investigations of how do we make a better mixer. So let me see if I can, there's one. The flow patterns in there are not great. Where'd my pen go? This is an example of like the way that we often look at or imagine flow patterns inside of a CSTR. So I'm just going to put this right on top of it. It's not uniform, right? Stuff can come in up here and sort of get caught in a loop and come out. Or it can come in quickly and fall way down and get caught in a loop down here and take forever to come out. Same thing on the other side. So these little bars that you kind of see over here on the side, these are called baffles. And so we often put obstructions inside of the tank to limit the number of times that something can get caught in a cycle like this and just sit there and spin around. It can be very tricky. You're welcome. Okay, that looks like everybody. I'm going to go ahead and stop recording. If you're watching on YouTube, we'll see you on Wednesday. Stay safe out there.